legal.
Tá dizendo. Agora tá
É
ligado.
porque Farinaldo falou que ia ser no Google Meet, né? Aí por isso essa...
O link será o do perfil.
Foi ele disse aqui, deve várias cerimônias.
Que coloca aí na outra parte. Bom dia, Clarissa.
Ver se tá. Olha pra.
Eu quero que ele ponha na.
Você não tá falando com ela? Tu fala.
Então, mas eu quero que você ponha lá para eu ver.
Ah, você quer ver o... Cadê aqui?
Perfeito. Beleza. Então, eu vou falar um pouco sobre esse artigo, né, que é um artigo envolvendo ondas gravitacionais em matéria escura do tipo 5. E aí, é para falar em inglês ou em português?
Eu já ia dizer.
Okay, I'll falar em inglês. So, I will talk a little bit about this paper, and basically it's about single order phase, first order phase transition, where we're gonna have the creation of gravitational waves background, and it will be related to a dark matter scenario.
Olha no
Okay.
como você fala.
Okay. So let me try to put this. So basically, we have the potential because we need to define two parameters to generate the spectrum of the gravitational waves. They are called alpha and beta, where alpha is related to the energy density generated by the phase transition, and beta is associated to some properties of the variation of the potential. But in this paper, they do not make it clear, but they define the potential because they will define a framework where we're going to have three particles annihilating into two another. So we have this, what they call 3-2-2. In this case, they just extend the standard model with a singlet, two singlets of scalars, and one of them is 5 will be the dark matter candidate in this work, and it will be stable due to a Z2 symmetry. But these 5 won't develop value, so just the scalar delta will develop a value, as well the Higgs doublet, the Higgs field in the standard model, as we know. Just a little bit. So it will be very similar as we already know, but we're going to have new parameters because of this new potential. So we're going to have some mixings between these scalars. And basically what we have to know is that which are the process that will generate the abundance of dark matter, and he puts in these 5 diagrams. So basically, that's the statement. And there will be at least 3 parameters which will be very important to calculate the Rayleigh bonus, which will be the lambda 11 and lambda 12, which lambda 11 will be related to the mass of the singlet, scalar phi, and the other will be related to the mixing between the interactions between this new singlet delta and the phi dark matter particle. So then they just put in the test, they put just the Boltzmann equation that will be related to this production of dark matter bonus. And basically the other equations is just telling what the way they are parameterizing the model and how it will generate the bonus that we observed. Okay, go ahead. Let me go to the right, what is really important, because here they were just saying that we have to make some perturbations in the potential in order to have in order to create these gravitational waves, and in order to have a phase transition of first order, we have to make some fine tunings in these parameters, because we don't want to generate a second order, because it will not produce a spectrum that could be observed by the future experiments like the Seagull and the others. I forgot. But that's okay. So here is one of the plots that they show. We have this benchmark models parameters of the model. So here we're gonna have, for example, lambda 11, lambda 12, lambda 22, 23, so on, and the masses of the scalars in this model, and the Rayleigh bonus, which is the right, which is basically what we are reserved, and also they show the benchmark parameters for the case of the gravitational waves generation, so say to the gravitational wave parameters. Here, as I said, it's alpha, and this is beta, but in general, they don't present beta as just a single parameter separated. They present generally as a ratio with the global parameter, because beta is the inverse of time, so this beta is time. Indeed, there is like a relation with time, so we're gonna have how can I say? Exactly. Non-dimensional parameter. So here is the parameter we showed now, and for the case of alpha, it will be related to this quantity. And here is the other plot where they present the plot given by the dark matter abundance and the related parameters to the dark matter mass, and which will give this cross section associated to the cross section of the dark matter. So they fix this parameter lambda 11 and calculate the dark matter abundance associated to the phase transition. Because it's different. Okay, I will explain further. And they also, for the same benchmark, they will calculate the spectrum of the gravitational waves and as a function of the frequency, and they will give this as a result. So they have to calculate the collision spectrum, how can I say, the sound waves, and also the turbulence. And after all, we sum all up, and we're gonna have the total spectrum. So as they say here, they will have observed relic density around the subject dark matter, which will be connected to the generation of this spectrum for gravitational waves, where they may could detect it in a sensitive associated to this value for the spectrum of the gravitational waves given by this millihertz region. So basically, that's what they did. And what about we are doing? We are doing something very similar, but first I will explain. Let me see. In our work, we're gonna compute. We do not generate our own spectrum of gravitational waves. We use some benchmark parameters of some model, which the model that we are working is a simple extension of the standard model for gauge variance symmetry, where we have V minus L symmetry, and this is associated to the Z prime boson, and we also have our arithmetic candidate is a vector-like fermion. So this is a very simple model, and we also have a scalar, which is a singlet, which will be related to the generation of the Z prime mass, and also it is okay. Here we're gonna have also a coupling, right? And in this case, this is the scalar that we're gonna have the potential, and we will generate the gravitational waves. So some people did in our work, they just computed the spectrums for gravitational waves for the case of this scalar, how they will generate it, and which is the parameters that we need to generate this spectrum. So for the case of particle physics, they have the lambda, which is associated to the potential of this scalar. They don't have dark matter in this case, and also they use the VAD of this potential, and also they use the V minus L coupling. And in the case of the gravitational waves, the parameters are the same that they use in this work that I showed. But in our case, we want to compute the dark matter bonus, the correct relic bonus, but we want to see what is the region of the parameter space that is connected to this gravitational wave spectrum. So, for instance, what we do is try to overlap both graphs, both plots, in order to see what is the region that are connected. So in this case, but we must take care, because here we are fixing these three parameters are fixing in this plot. And in the case of our computation,
Isso. Talvez seja melhor se fazer aqui embaixo.
in the case of our computation,
we have a question from Clarissa. She's asking, what is exactly this spectrum on gravitational waves? We may compute that as we compute the relic abundance.
No, it's computed using, it's not, how can I say? It depends on the frequency, which is related to the energy, but it's sometimes it can be connected, for example, to the generation of new degrees, relativist degrees of freedom, because it could be radiation too. But it is generated from the potential and a perturbation that we do in the potential, so it will be governed by a different physics. So we do not use Boltzmann equation to compute this spectrum. But what it means basically is that it's possible to connect the Rayleigh-Cabanis of this gravitational wave radiation, with some related frequency. So it's similar to what is done for the photons in the case of the BBN, but it is ruled by a different physics.
She followed up in her question asking if there is a kind of abundance.
Yes, it's similar to an abundance, but there is no. I mean, it's not it's a theoretical computation, so we don't have experimental value for that. So we are trying to find this background. It's a background radiation of gravitational waves. So it's similar to the case of the photons of CMB. So we expected to observe, because in this case, I didn't tell, but in this case we have some future possibly observations. So we have something like that, which is decidable or illegal. There's others. Sorry, they are already, but I forgot now the names. But there are many, and they will try to. This is future experimental interferometers. So they will try to reach the sensitive to observe a background of gravitational waves generated by some phase transition in the early universe. That's how we connect the production of dark matter, because everything is happening in the past, the early times. I don't know if that's right. Something more, Clarissa?
There's a delay.
Okay. So, but in this case, here in this parameter space, as I will try to recapitulate, to recap what I was saying. First, it's important to have in mind that here we're gonna have the VAV. I mean, all these parameters are fixed in this plane, but here we're gonna have changes. We're gonna change. We have to fix one of them. I mean, the first point, the mass. Any one of these parameters will depend on lambda. So it will not enter the situation. So it's outside some kind of 3D fold that we saw yesterday in the meeting, for example. So sometimes it could be, have something which will be very interesting to see something similar to that in this case. But I'm telling you today, and Alvaro knows also, because we was talking about some kind of, because here I just have a 2D parameter space, but maybe if we could have a 3D parameter space, we could see things, the real connection between these parameters. But okay, that's okay. So this parameter won't enter this plane, but this other will. So here we compute the correct Rayleigh-Cabanis. So we're gonna have different kinds of curves or shaded regions, but basically we may have, for example, something similar to that. But here we just saying that the cosmology, the early history is happening as we learn in the Lidus group, for example. And here the VAV is changed because the mass of the Z prime depends on the VAV. Depends on the value. So we're gonna have different values in these lines, horizontal lines, for different values. I mean, different vertical lines for different values of the value. So when we plot these both plots, when we overlap them, we have something similar to that. So if I have something like this, suppose if I have something like this, I would say, okay, we have a connection between them, between the correct Cabanas and the frequency of the gravitational waves, which in the first glance we would say that therefore there is a value of the cross section which is related to the z prime. The cross section is proportional to GBL squared over the mass of the z prime, basically in the resonance region that we are working here. So we would say, okay, there is a mass of the z prime, the guy that is a mediator, which is related to the production, which is related to a VAV, which is related to the production of gravitational waves in the early universe. But it's not so true because, as I said, not necessarily this region is entirely correct for both, because we are overlapping. And here we have just GBL is fixed, but the VAV is changing. So we have to take one VAV as they did for this spectrum, for example. So say, let's suppose that this spectrum is V2. So we're gonna have V2 going here. So only over this line, this Fourier space is valid. So the connection that we want to make. That's all for this case, just in order to understand what's happening. And I will show some. Just change here. Okay, here is, for example, for GBL, these values of the particle physics, GBL, and also the VAV is the same as the guys that computed the spectrum for the gravitational waves using. So here in this image, we can see everything together. So this line shows the correct Rayleigh-Cabanas. Here we have the LISA photo detection sensitivity. We have the SIGO, BBO, LIGO, and CE. But for example, that's a result that's very hot because I just take it in this morning. So in this case, for GBL equal 0.44, we're gonna have this spectrum of gravitational waves. We're gonna have these future detections. We're gonna have these Rayleigh-Cabanas, but the VAV gives just in this region. So the only set of points that will really be important in this setup, in this plot, will be in this black line. And in this case, here is the value that's connected to this spectrum, and here's another value which is related to the production of this spectrum, but they are very distant. See, so we expected that this value of the mass, the dark matter mass, would be producing this spectrum, which will be associated to this spectrum, but it doesn't necessarily is related to. And here we have the LHC. The LHC is excluding all this entire region before this line. I forgot to put the arrow saying that. And the Xenon experiment, direct detection, is excluding all this entire region here below this curve. And this is for a case of GBL equal to 4, but different value of VAV. I'm using exactly the values that they used in the other paper. So here I just put the value of the dark matter mass, a shaded region, just to see what is the value of the mass, which is around 200 to 2,000 GeV. And what we observe here, for example, is that there is a relation between them. There is a mass of dark matter particles that are really related to the production of this spectrum, which could be observed in the future, but they are not passing through the spectrum line too. So it's also, let me see a question from Clarissa. Yes, I'm asked the question that Clarissa is asking is, it's not clear to me why just this line works, and so it's impossible to connect gravitational waves with dark matter abundance, or they are not related. My question is, we need an overlap between abundance and gravitational wave spectrum to have a feasible model. First, the point is for this model and for this cosmology, that's the standard cosmology, we are saying that there is no relation, there is no relation between the production of the dark matter particles in this model and the production of gravitational waves in the early universe. Basically, is that what it means? And only this line works because the black line works because it's exactly over this line that we're gonna have the same values for the parameters fixed for both cases, for the case of spectrum of gravitational waves, and also for the case of the Rayleigh abundance of dark matter. So, as I said, I just obtained because this bounds on Xenon. It was I have obtained it in a wrong way, so today I just corrected it. But now I did it during let's see, the twilight. Okay, but I just obtained this bound, but I have to impose it in the others cosmologies, but I have already computed it. So we have here, for example, in standard scenarios, the calculation of the Rayleigh abundance for different scenarios in cosmology, where we're gonna have a early matter domination case for this purple, and we're gonna have for the gray line, we have early radiation dominated, which basically both scenarios are related to the decay of a scalar in the early times, and in this case, both Orange and red, we have the production of dark matter in a fast expanding universe. For these two values, these two parameters, n, which is related to the redshift of the density of the fluid in the early universe. But I won't explain it too much now. But if anyone has questions about this non-standard cosmology, I can answer.
How can you, because you have to do a lot of math to connect these kind of results to a production of a gravitational wave in non-standard cosmology, because
no,
you
it's
have
not
to change the whole math, because cosmological perturbations feels what is happening.
okay, but in the case of the production of, yes, I understand. But in the case of the production of gravitational waves, it's assumed that the universe,
Assume, all right.
That the universe is dominated by radiation at the time when the phase transition happening, the production of dark matter comes on.
Yes, but your current spectrum that you measure today, for example, for CMB,
will change.
CMB power spectrum, or for
I agree.
For matter power spectrum, because this is a matter power spectrum and a CMB power spectrum.
Yes.
It's different things, all right? So let's assume CMB, and the CMB power spectrum feels what's happening in the whole moments of the universe. So there are different peaks because different things are happening in different ages. So it's not so simple.
It's not, but it's already studied. So in this case, what happens? I will have to explain the cosmology. But it's not a change in the cosmology like phantom models, like FFR models. It's not something like that. It's just we have a window in the early universe, and we can change as we want, basically, in some range of temperature that we can make some.
I know. You are considering.
So
that
what happens is that in this case of this cosmology, we are considering bounds from CMB. So they are already constrained by CMB. So the temperatures that I am considering, the parameters that I am considering, they are encoded in the CMB bounds.
They do that?
Yes, because yeah, they do. I can show you. But because for example, in the case
what you show me,
in the case of these non-standard scenarios that we have n equal 2 and equal 4, for example, what we have is something like we have some new fluid, which is a phi, and it's proportional to 4 plus n. So for n equals 0, we're going to have radiation. But if we change the value of n, we put it equal 1 or more, we're going to have new fluids that will redshift faster. But that's okay. At the end of the day, we're going to have this guy, and we're going to also have something similar for the Hubble parameter, which will change in the case of the Boltzmann equation, and then we'll change the way that the dark matter particle will freeze out. We're going to have something similar to that, because for n equals 0, we're going to recover the radiation. And for n equals 2, we're going to have 1, for n equals so the way that we always have something similar to that, to the rate of the interactions in the thermal bath. And when we change the way that the Hubble depends on the temperature, we're going to have different kinds of results. So something like that could happen. And so the parameters affixed, the cosmology affixed by n and tr in this case. This is the cosmological parameters.
For cosmology in a zero-order perturbation, yes.
Yes.
But I'm saying that when you are leading with a gravitational wave, you have to come to one-order perturbations.
Yes.
And consider basically the tensorial perturbation. This is not so simple.
Yes.
This is not. I will show you
I agree.
in the next 2 weeks how I can do that, because it's something that I'm working on very hard, and I will try to give a more expanded ideas in this kind of things in the work. But the power spectrum is very sensible because it's a one-order perturbation. The power spectrum of a gravitational wave.
Yes, yes, I agree.
So it's very, very, very sensible because it's sensible to the first order perturbation.
Yes, I agree.
They can feel this kind of small changes in the universe.
Okay. We have another question from Clarissa, which is actually a pretty interesting question that I was thinking as well, which is, but why are you considering a non-standard cosmology if you have a viable region for dark matter in the other plot?
The first glance, we don't have exactly a valuable region because, as I said, it is the region just will release on this line, so it's not exactly here. For example, we have this point over the line, but it's not in this one because we have the match between these three curves: the line, the black line, the abundance, and the spectrum. So the idea to use new cosmologies would be to change the abundance in order to, for example, bring this curve to here, for example.
So basically what you're saying is that in this plot, there's no region where you can produce the right spectrum from gravitational waves at the same time that being not excluded by other experiments.
Exactly.
And producing the right relic abundance for dark matter. Okay.
But of course, I agree with you, David, because indeed it will be different. But we have to take a look more closely about that. But in the first glance, it's important to think about what we observe. So if we have just the CMB, and this cosmology won't change the spectrum of CMB, I hope it won't change the spectrum of gravitational waves.
Oh.
Because
they are a theorem in the relativistic.
No. Here.
I will present to you a Newtonian gauge, all right? I don't like other gauges, and if you like other gauges, it's your problem, not mine. So let's see the metric in the Newtonian gauge, all right? So I will use the signature minus, plus, all right? Because it's the usual in cosmology, all right? So here in zero order perturbation is that, okay? And I will call the small perturbation as 2a, okay? 2, fine, it's better. G0e is 0 in the Newtonian gauge. The other gauge can be a vectorial perturbation, but here we are not considering that. And here we have a scalar perturbation that I will call C. This is usual, this notation, okay? This is usual. And delta EJ plus what we call the TT perturbation. That is, okay, here. So we have what in the universe? We have radiation, is basically photons. We have neutrinos. We have baryons. And we have photons, neutrinos, baryons. Okay. All right? Is something missing here? And we have dark energy. There is no perturbation in dark energy spectrum because it's constant. Neutrinos and photons and baryons not, but neutrinos, photons is only sensible to two kinds of perturbation. The scalar perturbation. Scalar perturbation generate perturbation in the power spectrum of photons. For example, if you remember, let me see if I remember. I think is the P. No, it's 1 over exponential of P over T. I never remember if plus or minus here to photons. I think it's minus 1. This is for usual photons, okay? Here because there are no masses. But when you introduce this kind of perturbation, this tier became T1 power spectrum of photons. And this power spectrum of photons are correlated to these both.
Okay.
There are no relation between the CMB power spectrum and the gravitational wave perturbation. Both are independent. They are not connected. There are a very, very powerful theorem in general relativity that scalar, vectorial, I'm not considering vector perturbation because they do not survive in the Newtonian gauge, okay? In other gauge, maybe, but in the Newtonian gauge, this kind of perturbation do not survive. And tensorial perturbation that generates gravitational waves are completely independent. So there are no reason to consider it. If this is irrelevant, this is also irrelevant. You have to show that. Maybe they show, but you have to show because they are not dependent one with other because of the Einstein equation. Who proved that was Lifshitz. I think it's this. It's because there are two Lifshitz in physics, and they both are brothers, so I don't remember who made that.
But at the same time, we could just think, because if we consider that the production of gravitational waves happens before the time of the CMB,
okay.
So we're gonna have different. How can I say? Because the production of the CMB is also related to the at first order, as you say, in gravitational waves, but also it's in different times.
Yes, but what we measure is today.
Yes, I see.
So the gravitational wave feels.
The temperature of the photons, of course, is related to the potential, the gravitational potentials that existed at that time. But I mean, I'm agreeing. I agree with you. That's not the problem. I'm just trying to remake my sentence and supporting myself. because maybe it really changed this.
It's not. You can be right.
It's not too easy, indeed. I mean, it's not simple. Not simple. Just say that.
No. Because if you any change here, we have to do the math.
Yeah.
I will next presentations. I will explain this kind of mechanism in details because it's a thing that I'm studying. But I was only trying to explain that this kind of assumption is not really true. It can be, but it's not really true, all right? It's first order perturbation. Second order perturbation usually is only used to study baryons power spectrum. Okay?
Okay. Nice. So, I think it's basically what I had to say. Okay. Oh, I finished the presentation. That was what I had to say. The president and David gave a very important contribution because David is in the work also, and and I am just doing the first things. But of course, we have to make some deep analysis and some discussions also. But basically, that's what we have so far.
Thank you.
So goodbye, everyone. See you next week.
And